Alright, so correlation is what we're going to talk about today. It is a measure of association between two continuous variables. Usually we call those x and y for scatter plot kind of situations. And one of the key things about correlation is that it is measured on the same subjects. So if you're measuring height and weight, it's on the same people. You're looking at how many people go to a school and what their tuition is. It's on each of those pairs of numbers goes to the same school. So you can't measure a correlation between test scores in one class and test scores in another. That's not possible because there's no link between any two people. Correlation is a measure of association. It measures how much y, one of the variables, differs from the mean when x differs from the mean. It can be driven by an underlying cause. So we're going to talk about ice cream and crime and pirates and temperature. These are both things that have correlations with each other, but it's not because of a direct relationship. So what do I mean by that? I'll show you in a second. So we use a scatter plot to represent correlation, and I'm going to change the order of this slide when I redo this lecture. And yeah, each dot's a data point. That's one person with a measure of x and a measure of y. So here's the ice cream and murder rate data. This is a real thing that you can find, and then you see that as the murder rate goes up, the number of ice cream sold goes up as well. And so this could be because people are eating ice cream because they feel stressed about murders, but more likely it's because these are hot days where people are out in the street. These are cold days when people are inside, and this is Chicago, so that people eat less ice cream in the winter and are more likely to be on the street shooting each other in the summer. This was in New England. The murder rate and ice cream sold would be horizontal because people in New England eat ice cream all year long. Similarly, here is a global plot of how many pirates there are in the world, labeled by year, and what the average sea surface temperature was in a particular year. And you can see that there's this decline. So if there's a causal relationship, for example, if pirates were so cool that they cooled off the world, then this would be the cause, but more likely the underlying thing is good times. The underlying thing is that there is a industrialization factor going on here, where more industrialized means more global warming, and less industrialized means harder to keep pirates under control. So one of the things that correlations math results in is that U-shaped relationships like this, which you and I would look at and say there's a clear relationship between x and y here, that would have a correlation of 0. So you can only have straight line associations. If there's just as x goes up, y goes up. So there would be a positive correlation in this part, a negative correlation in this part, but you look at this whole thing and they cancel out, so there's 0. So the numbers of correlation go from -1 through 0 to +1. So 0 is no association, +1 means a straight line going up and right, -1 means a straight line going down and right. And if you square the correlation, you get this thing called the coefficient of determination. So that's going to always be positive. It's going to range from 0 to 1. And it's a measure of how strong the relationship is. And it's actually quantitatively the proportion of variance in y divided by x and vice versa. Which means that there's shared information between the two of them. If we know that x is a little above if they have a high correlation, if x is above the mean, then y will be above the mean also. So here's some examples of strong and perfect positive relationships between variables. So this would be like a 0.7, and this would be a 1. Here's a strong -1. This would be like a 0.8 or so. I'm sorry, -0.8. Here's some more examples. So this isn't perfectly straight, so that weakens it. So this would be about a -0.3. Strong positive, about 0.8. So it's kind of football shaped. No correlation, and that's a typo. Let's fix that. And there goes my dog in the background, good times, and there's a negative 0.8. Sorry about that being, I should fix that as well, I will. Okay. So one of the cool things about correlation is you can have multiple things measured on each person, and then you can see how each of them correlate with each other. So income is correlated with itself perfectly, that's a 1. So strong positive correlation with income and education. Whatever attitude they're measuring doesn't really relate to income at all, and how they vote is negatively related to it. So you can pick through and see how things are related. Note that this is symmetrical. So this 0.08 here, negative 0.08 here, is across the diagonal from this one. This is the diagonal here. These are symmetrical. So all this data up here is repeated below here. So when we do hypothesis testing for correlation, we have a null hypothesis. There's no correlation between these variables. And our research hypothesis, there's significant association between the variables. So some data I did. I generated 12,000 different pairs of random normally distributed variables with 10 observations each. So the correlation should be 0, but you can see that sometimes just by chance there was a correlation up here close to 1. Sometimes by chance there's a correlation with -1. So even if there's no true correlation underneath them, you can still get a range of correlations. So we take this correlation, we multiply it, we scale it by the standard errors, which are a function of the correlation. The closer the correlation is to 0, the bigger our standard error is around the correlation. And so we get these correlations divided by the standard error, we get a t-statistic. So there's our t-statistic, and we're going to, the degrees of freedom for our t-test is the sample size -2. So just like single sample t-test, we have one thing we're comparing to 0. But it's not a mean, it's a correlation. Then talking about tails, if we're only interested in a positive correlation, then a 0 correlation or a negative correlation is non-significant. If we're only interested in a negative correlation, then a 0 correlation or a positive correlation is non-significant. And if we don't know what the directional relationship is, we just want to know if there's any kind of relationship at all, then it's two-tailed, and either of these are significant, and the stuff in the middle is not significant. So this would be like if we're interested in looking to see if there's an improvement, if there's getting worse, or if there's any change. So again, use 0.05 as our magical alpha value, and that tells us whether the variables are associated, but we also need to look at the strength of the association to see if it's meaningful, because if you have a really big sample size, you can have an association that's significant but not necessarily meaningful. So if you have a correlation that's 0.628, sample size is 21, and the variables are foo and bar, you'd report there's a significant positive correlation between foo and bar. And say little r is the symbol for Pearson's product moment correlation coefficient, and the degrees of freedom, which is the sample size -2, and the correlation and the p-value. Okay, let's see if this helps.